Good day, students. Module 4 is about periodic relationships among elements. In this module, we are going to discuss 3 lessons, which we start with the development of the periodic table of elements. So how did the modern periodic table of elements came about? In ancient times, scientists don't know yet about element, or they don't have yet the clear definition of element. It was in 1789 when Antoine Lavoisier defined element, or gave a clear definition, an accurate definition of element, which is a substance whose smallest units cannot be broken down into simpler substances. So with this definition, he was able to publish a list of 33 chemical elements, which he grouped into gases, metals, nonmetals, and earths. Now, in the 19th century, chemists don't know yet about the subatomic particles like the protons, the electrons. At that time, though, they already have accurate measurements of the atomic masses of the elements. So they thought that the chemical behavior of elements should somehow be related to their atomic masses. So according to them, the elements in the periodic table should be arranged based on their atomic masses. For instance, we have Johann Wolfgang de Bruiner, who in 1829 proposed the law of triads, which states that the weight of the middle element is nearly the same as the average of atomic weights of the other two elements. So here we have an example of de Bruiner's law of triads. As seen in the slide, we have here de Bruiner's triads of elements. So in the first triad, for example, we have lithium, sodium, and potassium. The atomic mass of lithium is 7, while that of potassium is 39. If we get the average of the atomic masses of lithium and potassium, we have 7 and 39 over 2, we get 23, which is actually the atomic mass of sodium. Another example, for the second triad, we have calcium, strontium, and barium. Calcium has atomic mass of 40, barium has atomic mass of 137. If we get the average of the two, we get 88.5, which is actually close to 87.5, the atomic mass of strontium. So that is how de Bruiner grouped the elements in triads. Now the problem with de Bruiner's law of triads is that not all elements can be grouped this way. In 1862, Alexandre Champcourtois noticed that the elements, when ordered by their atomic weight, so he still used atomic weights just like de Bruiner, he noticed that they displayed similar properties at regular intervals. So he devised a 3-dimensional chart named the telluric helix. So like this helical structure, which is named after the element tellurium, which fell near the center of his diagram. So with the elements arranged in this way in a spiral on a cylinder by order of increasing atomic weight, de Champcourtois saw that the elements with similar properties lined up vertically. For example, we have lithium and sodium, which have the same properties lined up vertically, and we have beryllium and magnesium. In 1864, British chemist John Alexander Newlands arranged the elements in ascending order of atomic mass, so still using atomic mass, and discovered that every eighth element exhibits similar properties. So he called this the law of octaves. Newlands compared the arrangement to that of the octaves of music, do, re, mi, fa, sol, la, ti, do, where every eighth note is compared to the first, or is comparable to the first. So shown in the figure, hydrogen, our first element here, is likened to a lower do, musical note in the octave. The eighth element, so we count 1, 2, 3, 4, 5, 6, 7, 8. The eighth element, fluorine, is likened to a higher do, musical note of the said octave. Now hydrogen and fluorine were found to exhibit the same properties. Now starting from fluorine, we count 8 again. 1, 2, 3, 4, 5, 6, 7, 8. Our eighth element is chlorine, which also share the same property as fluorine and hydrogen. Now the problem with Newland's law of octates is that after calcium, every eighth element does not possess the same property as with the first. For example, as shown in the figure, so starting from chlorine, have 1, 2, 3, 4, 5, 6, 7, 8. The eighth element could be or is either cobalt or nickel, and they don't have the same property with chlorine. So Newland's work was not accepted by the scientific community. In 1864, German chemist Lothar Meyer noted sequences of similar chemical and physical properties of elements repeated at periodic intervals. So he published a table of 28 elements which are arranged based on their valence, the outermost electrons. In 1867, German-American chemist Gustavus Henrichs published another spiral periodic system, which is also based on the atomic weights of elements. So here is an example of Henrichs' periodic system with the elements in a bicycle wheel form. The system looks like a bicycle wheel with the groups of elements displayed as spokes. So these are the spokes, the vertical lines here, this one here. As you can see, we have our halogens, for example. This is one group. Another group here, we have our alkali metals, lithium, sodium, potassium, and rubidium. In 1869, Russian chemist Dmitry Mendeleev and German chemist Lothar Meyer independently proposed a much more extensive tabulation of elements, which is based on their regular periodic recurrence of properties. So the elements are still arranged in the order of increasing atomic weights, though some gaps were left blank for the elements not discovered at that time. Unfortunately, you may not have heard of much of Lothar Meyer. It's Dmitry Mendeleev who is famous, no? So what happened was Meyer's work wasn't published until 1870, a year after Mendeleev's 1869 periodic table. So his contributions are overshadowed by Mendeleev. Dmitry Mendeleev has this periodic law, which states that the properties of elements are periodic functions of the periodic weights. So when we say periodic, it means occurring at regular intervals. So basically, the periodic law of Mendeleev means that the physical and chemical properties of elements reoccur periodically when the elements are arranged in the order of increasing atomic weights. Now, Mendeleev's classification system was a great improvement over the previous ones. Firstly, because it grouped the elements together more accurately according to their properties. For example, we have the halogens, fluorine, chlorine, bromine, chlorine, bromine, and iodine grouped together. We also have the alkali metals, sodium, potassium, rubidium, cesium grouped together already. Secondly, Mendeleev's periodic table made possible the prediction of the properties of elements which were not discovered yet at that time. For example, Mendeleev proposed the existence of unknown elements that he called Eka aluminum and Eka silicon, and predicted a number of their properties. So when we say Eka, it's actually a Sanskrit word meaning first. So thus, Eka aluminum would be the first element under aluminum in the same group, and Eka silicon is also the first of its group. So here we have our aluminum, for example, and silicon. So here we have our question mark, that what would be the element next to aluminum and next to silicon. Okay. Here is Mendeleev's prediction of Eka aluminum properties. Again, we say Eka aluminum. Aluminum is the first element of that group. So Eka aluminum, that would be the next element in that group. So here are the properties of the Eka aluminum. What happened was gallium was discovered 4 years later after Mendeleev's prediction of Eka aluminum properties. And true enough, its properties match the predicted properties of Eka aluminum remarkably well, as you can see in the table. Here we have our gallium properties. The atomic mass are very close in amount, the density as well as the formula of the oxide. And true enough, in the modern periodic table we use, gallium is next to aluminum in the group. Shown in this table is Mendeleev's prediction of the Eka silicon. So when germanium was discovered in 1886, its properties matched with Eka silicon. So here is the properties of germanium compared with the properties of Eka silicon. In the modern periodic table of elements we use, germanium is actually next to silicon. So Dmitry Mendeleev's predictions were correct. Although Mendeleev's periodic table was a celebrated success, the early versions had some glaring inconsistencies. For example, the atomic mass of argon is 39.95, which is greater than that of potassium, 39.1. Now, if elements were arranged solely according to increasing atomic mass, argon would appear in the position occupied by potassium in the periodic table. But no chemist would place argon, an inert gas, in the same group as lithium and sodium, which are very reactive metals. So they don't have the same properties. So therefore, there must be some fundamental property other than atomic mass that must be the basis of periodicity. The problem was solved by Henry Moseley, who in 1914 discovered atomic number based on the X-ray wavelength of the element. So then he arranged the elements according to increasing atomic number. Take note that the atomic number is also the same as the number of protons in the nucleus of the atom. So with this increasing atomic number, the elements with similar properties are repeated after a regular interval. Take note that before Moseley, the elements are arranged in order of increasing atomic masses. So it was Henry Moseley who arranged the elements according to the atomic number of the elements. Now, with a few exceptions, Moseley found that the atomic number increases in the same order as atomic mass. For example, calcium is the 20th element in the order of increasing atomic mass, and it has also an atomic number of 20. Now, the discrepancies that had puzzled earlier scientists now made sense. Remember the problem with argon and potassium? The atomic number of argon, he found out, is 18, and that of potassium is 19. That is why potassium should follow argon in the periodic table of elements. And this is how the modern periodic table of elements looks like now. In this table, we have the atomic numbers here, for example, and the symbol of elements shown.